Good day, folks, and welcome to our webinar presentation. My name is Adam Harris, CEO here from C-Therm Technologies. Great pleasure to be with you today. I'm going to be joined shortly by my colleague Arya Hakimian, an application scientist here at C-Therm, and Dave Dale, a product manager from SciMed. This webinar is part of our launch event, bringing together a new partnership, a collaboration between C-Therm and SciMed in the UK and Ireland. We're really excited about this new collaboration. C-Therm is an expert in thermal conductivity testing and measurement. We focus on applications ranging from electronics to geological to consumer goods, sporting goods, textiles, really broad range. And we'll talk a little bit about some of the innovation we're driving in that space today. But I'll speak also just a little bit to this partnership, which is new with SciMed. What I'm particularly excited about here is how this is going to translate to better support for our clients in the UK and Ireland, better pre-sale and post-sale application support. SciMed is a group that's been around for a long time, has a lot of experience in thermal analysis and other areas adjacent to thermal conductivity testing. I love the workshops that they run. They really focus on really helping push education in the industry and upskilling with very hands-on oriented events hosted at their beautiful facility. We're going to be scheduling some of these later in the year on the topic of thermal conductivity. But this event today is really just to kind of make this announcement, welcome SciMed to the C-Therm family, and talk a little bit about some of the innovation that we're driving in the space of thermal conductivity measurement. So today's session should run for approximately 45 minutes to an hour. We'll reserve a little bit of time for Q&A towards the end of the session. I'm going to be introducing SciMed here shortly. Dave Dale, a product manager from SciMed, will join us and introduce their group's experience and talk a little bit about some of the work they've done. And then we're going to pass it over to Arya Hakimian, my colleague, who's going to take us through some of the areas that are trending more prominently in terms of thermal conductivity characterization. What are some of the specific needs of these types of applications, and how does C-Therm help researchers in these areas advance their body of research as it relates to thermal conductivity? So we'll talk about aerospace and defense, which is certainly an area of growing interest and priority around the world. We'll talk about heat transfer fluids, including their extension into use in data centers as a coolant. We're seeing more and more power density and heat build up in these data centers. And so what strategies do you apply to cool them? Immersive cooling is starting to become more and more prevalent. We'll talk about some of the work we're doing in textiles with leading brands in this field. We've worked with all of really the top athletic brands to quantify that performance from a thermal perspective. We'll talk about geothermal and geological testing, both from a oil recovery basis, oil, of course, being a very important topic the last few weeks as we're seeing that surge in pricing. So how is this used in enhanced oil recovery and geothermal mapping and so forth? And then we'll wrap up some work that we've been doing, really leading the way in hydrogen research. So C-Therm has a unique capability when it comes to testing under hydrogen pressurization. And this overlaps really nicely with another one of SciMed's principles, PAR, that does a lot of the pressure reactors and vessels. And C-Therm has been working with PAR for a number of years on developing custom solutions for the hydrogen research market. So that's a quick overview in terms of the agenda for today. If you're new to C-Therm, and I see a number of folks on the registration, some of our partners from, I see Portugal, I see the Czech Republic. Thank you very much for joining us. But also a number of new clients and groups that are maybe less familiar with us in the UK. And so I want to welcome you, especially. As background, C-Therm is a Canadian tech company. We've been around for almost 20 years. We spun out of the University of New Brunswick, Faculty of Chemical Engineering. Our raison d'etre in life is all about simplifying thermal conductivity measurements. So that's our core reason for being. Um, and at that, I would argue we're the best in the world, especially when it comes to the transient methods for thermal conductivity. So I'll talk a little bit about transient, but really my colleague Arya, who's going to join us shortly here, he will go into the methods in more depth. But that's a little bit of background on C-Therm technologies. Our core product is the Trident thermal conductivity instrument. Trident was launched about 6 years ago. It's done fantastically well for us. It's all based on one single platform, a very advanced data acquisition system, and it leveraging the ability to offer clients multiple methods for thermal conductivity. The single biggest mistake I've seen over 20 years, repeated time and time again, is taking a good method and applying it on the wrong type of sample. And that's how you get bad data. So what we did with the launch of Trident is really try to recognize this, that a toolbox approach is much better. You're going to optimally use different methods based on the application or material you're looking to test or the application conditions you want to represent in that testing. So with C-Therm's Trident, it's multiple methods for testing thermal conductivity. Our philosophy is it's better to have options, and Arya will take you through and highlighting some of these different methods as we progress. But I love this quote from Abraham Maslow. He wrote the hierarchy of needs. You might remember that from an organizational behavior course in university. But I just think this really encapsulates the value proposition to Trident very well. We're living in a time in the world of like incredible change. The pace and velocity of change is never been greater. And so when we're putting in these types of capabilities, I think you really have to be cognizant of we don't always know what's coming down the lab's pipeline next year, what type of material, what different scenarios we might be facing. So it's really good to have something that's versatile and that can deal with all of those different types of application conditions and materials. This quote from Abraham really captures it well. When all you have is a hammer, everything looks like a nail. And that's the problem that often propagates in the space we operate, which is taking a good method and applying it on the wrong type of sample. We co-authored a publication on this. It's a rich resource on taking you through all of the different application methods for thermal conductivity, including steady state, transient methods, some of the oscillatory methods like FDTR, TDTR, which we have a great webinar coming up later this month with another one of our partners. But if you're interested, if you're just new to thermal conductivity, you're recognizing this is something you're going to need, I encourage you to scan the QR code or click the link that Carter's going to drop in here. A shout out to Carter, who's helping us organize today's event. He'll be operating the chat as we go, so you've probably already seen some comments in there from there. But great resource, encourage you to check it out. All right, I see Dave Dale has joined me online. Welcome, Dave. Pleasure to connect. Dave and I will be visiting some clients in early April. I'm coming over to the UK here in a few weeks, and we're going to be doing the rounds, visiting some different groups. If you are particularly interested in a visit, please put that in the chat box. We'd be very pleased to connect with you. But let me introduce Dave Dale. I'm going to stop sharing at this point so he can bring up his slides. Dave is a product manager at SciMed, decades of experience in thermal analysis and material testing. Had the great pleasure. Dave was over here a few months ago in the onboarding and training. Real pleasure to work with. He brings a lot of that experience and expertise into the conversations and very complementary other product lines like C-Therm, like PAR, that I think really create a lot of synergy in the relationship with SciMed, you as the customer, and C-Therm. So with that said, Dave, I'll pass the baton to you. Pleasure to welcome you to today's event.
Okay, thanks, Adam. Thanks very much for the kind introduction. It sounds like we have a lot to live up to, but that's great. Thank you very much. I just want to give a few slides on SciMed itself. Some of you may know us already, some of you may not. So I just wanted to give you a quick overview of SciMed itself and a little bit about myself, just to show how we're going to work with C-Therm going forward. So SciMed is an instrument distribution company. We're based near Manchester in the UK, and we were actually formed in 1979. So we're coming up for 50 years. So it's been around for quite some time. It's been growing, since that period, and we're now up to about 40 people, a mix of office, service, sales, product managers, marketing, etc., etc. So we have the full gambit of people in our offices. And we primarily serve the UK and Ireland markets, although we do sell some of our products into mainland Europe as well, depending on the agreement we have with the supplier. But the bottom line is our real motto, written in red there, is global products, local support. That is, and I'll come back to that tagline again in a moment. Just remember that. That's really summing up what we're about at SciMed. So for those of you who have never been to SciMed or perhaps haven't been to Manchester, this is just a few images of what we look like. So on the top left, you can see a lot of people. That's most of the staff at SciMed outside our building. About, I think it's 18 months ago, we actually outgrew the building behind us there, and we actually spread into another building on the top right here, which is actually just across the car park from the original building. So we have two buildings separated by a car park. And that's what they look like. And in those buildings, we'll say we have full facilities of office staff, stores, etc., etc. But the ones that may be of interest to you, so the bottom left and the middle picture here, we have demonstration laboratories in one of the buildings, and there's just a couple of snapshots of some of the instruments being set up for demos on those pictures. So we're able to offer full demos of most of our products at our facilities. And in the pictures on the right here, you can see some people at meetings. So as Adam says, we do a lot of seminars and workshop type days, and we have a couple of meeting rooms in the building where we're able to do this. One holds about 40 people, the one slightly less, but we can tailor those to what's required. But it's something we do hold quite regularly throughout the year on a variety of topics. So please look out for those, and if there's something of interest, you're welcome to come along. A little bit about myself. So I've been with SciMed since 2011. So actually quite some time now. My background before that, I actually worked in the pharma industry. I actually worked with a lot of thermal analysis equipment in the pharma industry, but I joined SciMed, as I say, in 2011. And I'm, as Adam said, one of the product managers. So what we mean by a product manager at SciMed is we don't have, as you'll see on an upcoming slide, we do have a whole range of global suppliers we work with, but our salespeople do not work across the whole line. We have product managers, I think it's something like 12 of us, who are dedicated to a specific subset of those products and become experts, technical resources for those products. For myself, I look after the thermal analysis products. So thermal analysis we work with a company called C-Therm, some of you may have heard of, a French company offering a whole range of thermal analysis instruments. I work with another company in the US, Fauski, who do adiabatic calorimeters, and another company who do specifically on high mass TGA. And of course, what we're about today, new and excitingly, we've now joined forces with C-Therm, and we're now able to offer thermal conductivity or the C-Therm products into our portfolio. And it has a great fit with what we do already, as you'll see in a moment. So just briefly, this is logos of most of our suppliers. I think there's nearly 40 on there. So you can see a whole range of instrument types from across the world. And I've seen C-Therm's ring has now been added to that list. Again, but I'm stressing it's global products, local support. These suppliers from all across the world, but we are able to offer you the local support that you need as you embark on these products. I've ringed C-Therm and PAR. Adam sort of briefly alluded to these earlier. because these products also have some synergies with what we're doing with C-Therm. And if I show some last slide here. So on the left is the Cetaran products. There's a whole range of thermal analysis instruments, DSC, TGA, calorimetry, obviously operating in the thermal analysis field, which is greatly works in conjunction with the C-Therm products as well. So great synergy there. And on the right, we have the PAR. So actually, PAR was actually one of the first, probably the first actually, it was before I joined SciMed, but the first company that SciMed acted as a distributor for. So certainly over 40 years for PAR. And we do a whole range of standard kit and customizable pressure vessels for there. And of course, at the bottom here on the left, you can see the Trident instrument, as Adam already showed you, and it's coupled to a PAR pressure vessel here for doing pressure measurements. So again, demonstrating how a lot of our product lines overlap and in great synergy between the two. So that's all I really want to say about SciMed. It was just a very quick introduction. Just to summarize, SciMed are really excited to be working with C-Therm. It's a product that greatly enhances our portfolio of thermal analysis products. And I'm now going to hand back to Aria, who's going to give you obviously the crux of the webinar and the technical details, which is probably what you really want to get onto. So thanks very much and enjoy the rest of the webinar.
Awesome. Thanks, Dave.
Okay, I'll just stop sharing.
Perfect. All right, folks. So yeah, as was mentioned here, I'm stepping in at this point to really walk through some of those application areas that we've seen really, I'd say, popularized in recent times. Starting out, we're going to jump right into them, kind of go through them one by one. And the idea here will be to really address what are the aspects or challenges in these spaces, what methods are best applied there, whether that's, again, related to the specific samples, the testing conditions, or almost more importantly, why are you needing thermal conductivity? Is this for quick comparisons in early development? Are you doing technical data sheet certification? All of these factors can introduce some reasoning as to which methods are most appropriate. So starting out here, aerospace and defense. Thermal management in this space is extremely important. When we're looking at thermal management considerations, something that you might want to maybe position in your mind is that, yes, a thermal interface material, for example, used in they're used in more advanced applications as well as your traditional consumer goods. But where there's the difference is what they're being designed for in their longevity. Something like a phone might be wanting to have 5 to 7 years lifetime. But if you're comparing that to something in, again, like a military and defense, avionics, these need to have reliable performance for many, many years, 25 plus years, often in extreme environments. And in some cases with, some of the autonomous drones that are being developed, without any opportunity for real maintenance. So there's a level of, let's say, safety factor that needs to be built into these systems as they're being developed. Again, I mentioned TIMs, so thermal interface materials. Again, this isn't unique specifically to this industry, but it is probably one of still the most, I'd say, studied and also important aspects of these thermal management system designs. Aging in some of these systems are things that can be quite detrimental. Whether that's related to some, off-gassing effect, changing of the bond line after thermal cycling. And the risk that people run into is that if you just, let's say, take the technical data sheet value as gospel there, you're not really seeing how that material may perform over the longer term. These TDS values are reported under ideal conditions, in controlled lab environments. But what happens when they start behaving in a non-ideal way? How do we quantify that? So these are some of the questions that can come up and introduce some interesting points in terms of method design and testing requirements in this space. So, kind of a takeaway point here is you want to have accurate and repeatable characterization, not just at the inception of the product or the development of the material, but understanding how it's going to behave over time, testing it under different environments, different conditions to ensure that it will be reliable when it's needed. So one of the application examples I'm going to share here, case highlight, is thermal mapping. This is one that if you've been on webinars in the past, you've probably heard me talking about this, but it is still in 2026 a conversation I have on a weekly basis with folks. Anytime you're dealing with a material like a thermal interface material or a polymer composite that is introducing some additive, if that material is not uniform in its dispersion within that matrix, you can run into issues. Again, in TIMS, this is hot spots, reduced thermal performance, and all of that can lead to, of course, safety, performance risks, but safety risks as well. So if you're new here, what is thermal mapping, you might ask? So in the example we're showing here, this is a polymer with a conductive metal nanoparticle actually that was mixed in. Just by looking at this though, you would, I would say easily be able to pick up on the fact that this is not homogeneous. There's a very clear non-uniformity in how that filler, that additive has been spread within that polymer matrix. But this is really just to demonstrate how the MTPS can work, because oftentimes the TIMs or the polymers that you're working with, they're opaque in nature. You can't see visibly these issues as clear as what we're showing here. So in those conditions, what do you do? So this is what we call thermal mapping. By taking the MTPS, which has an active area of about 18 millimeters on the face of the sensor, you can place that at different locations across the surface of your material. And then very quickly, within under a minute at each point, get a value for the thermal conductivity at those locations. And what this thus gives us is the ability to very quickly screen and understand the level of consistency, or, in this example that we're showing here, the lack thereof. So I mention this because this is a really critical step and really important to do, I'd say more so in that early development stage, to allow for that iteration velocity to essentially be done in a way that you're identifying these issues earlier on so you can mitigate them before you get to full product release. Now, of course, there's the ability to do this in QA/QC applications as well, like in different stages of development or in the product life cycle, I should say. But by and large, early stage development work, thermal mapping is, I would say, a very important aspect to consider if you're dealing with fillers or additives of any kind. Now, especially when we're talking about, as we kind of talk about the TIMs and some of these advanced material spaces, graphene, graphite-based materials, very novel materials are sometimes being introduced into some of these systems. But the challenge becomes the more novel the material, oftentimes that introduces more challenges in how do I go about testing it? Or if I test it with method A, what are these results actually telling me? So one such material are these pyrolytic graphites, high K in-plane heat spreaders. Now, these materials are, again, amongst some of the highest thermal values that you can get measured. But what the challenge becomes is they're often quite thin. And when you look at traditional methods, even some of the basic transient methods for measurement, there are certain requirements on thickness. This may be into the millimeter, or even some methods might be into the centimeter range. But if you're dealing with a high high K graphite heat spreader, they might be sub 1 millimeter. They could be in the micron range. So how do we measure that? So this is actually done with our TPS, specifically the slab utility, which is a version of TPS testing that can accommodate thinner sample formats. And here we can see some of the data. We're kind of separating out some of the different forms of the material. There was a few different samples that we tested in conjunction with the HPMS graphite that provided the materials. So there's flexible graphite, but again, pyrolytic foils ranging in thickness and density. But you'll see here, like up just shy of 1800 watts per meter Kelvin. There's a lot of times where you'll look at theoretical values for some samples, again, they're in the thousands. But less often do you actually see measurements truly produce results this high on actual test data. So this is a really great example of a novel material introducing some exceptional thermal properties, and again, providing a fairly straightforward path of testing using the Flex TPS and the slab utility. Moving forward here, so we've talked about some of the different areas of TIMs in this space, but kind of what the TIMs are often in there to help cool down these electronic components, but also the batteries. Thermal conductivity of battery pouches is something that is very, I'd say, popular. Again, you could look at this in the EV industry, but of course, again, some of these avionic systems, batteries in some of the defense, military side of things. Understanding the performance of that battery with respect to its thermal conductivity is quite an interesting aspect to investigate. And this is some recent work that was done here, again, featuring the Flex TPS to characterize a pouch battery cell. So these pouch cells, again, they can have different chemistries, but they generate heat during the charging and discharging. Poor thermal conductivity in that cell stack. This is where, again, you can run into issues where you see, like on the news, batteries catching on fire. Well, again, that could be applied in any context here. So thermal conductivity really does become a critical aspect of how do we ensure reliability in these systems. Now, the challenge with something like this is based on how that cell is constructed, you're getting this layered effect resulting in anisotropic material behavior, where you're going to get quite a different through plane thermal conductivity compared to the in plane. Now, when we look at TPS in a traditional measurement sense, you typically require two pieces of material, one to place on top and the other on bottom around a sample. Now, in some scenarios, this is quite straightforward, but oftentimes when we're testing a more complex system like this, that can be a challenge. So the data shown right here is actually done on our Flex TPS in the single-sided configuration, but measuring the anisotropy using the anisotropy utility. So it's a single-sided TPS anisotropic measurement. And as we can see, the difference in that axial, or view that the through plane thermal conductivity compared to the radial or the in plane is quite significant. Quite a large difference was noted here. And interestingly, this is an important thing to flag, because if you treated a sample like this as let's say, an isotropic material, well, we actually did that. So we measured it with the bulk utility, which assumes it's an isotropic, so it kind of averages out that in and through plane direction, gave a value of about 5. So this is really important in understanding, one, if the material is directionally dependent, what does that mean in terms of the measurement that I'm doing, and understanding how best to quantify the material based on the methods available. So the kind of for these battery applications here, especially the pouches, the TPS single-sided utility with that anisotropic capability provides quite a lot of benefit here to be able to quickly quantify the performance of these cells. And I thought I'd end the aerospace and defense section with actually some data that was presented at a conference here, the TFAWS cryothermal paper session. This was some work presented, I believe it was 2024, by Siddiq Malakuti from NASA. And here they're looking at some of these cryogenic insulation applications, again, for aerospace, specifically for space exploration and travel. So interestingly, in this paper, you can kind of see their setup here. They have, they were using our TPS sensor inside of this quite novel, basically cooling chamber, to take the materials, in this case, these aerogel type samples, down to cryogenic temperatures to quantify that low temperature performance. And just kind of wanted to share the data here, but it was a really nice data set looking at how they're able to measure these different types of materials. Again, very low K insulating materials, excuse me, down from about -20 all the way down to about just shy of -140 there. But kind of really nice showing that the trend, the differences in these different materials to help, again, further that understanding of the thermophysical properties of some of these aerogel materials, which, in some cases may be lacking some of this expanded temperature range data. So really nice data here coming out from this work to help expand that body of knowledge. So the next area, heat transfer fluids. As Adam had mentioned, really the focus here is on like data center cooling. With the developments that are going on with AI, I mean, you think it gets to a point where it's going to kind of start to plateau, and then at the beginning of 2026, you hear about new developments coming out, which are of course pushing the power requirements, the energy consumptions even further. But from a technical side of things, from a technological advancement, that is great. But then you have to realize on the infrastructure side what's going on, and this is just leading to more heat being generated. So you can kind of see this was some data from, I believe, 2024 again, looking at trends in energy consumption. This insight said, AI chips represent like a 1.5% of global electricity over the next 5 years. I wouldn't be surprised if that figure has actually even been updated since then. But again, it's a reality that we're living in that these data centers are consuming energy. And when we look at where that energy is actually being used for, it's in the cooling. So in this graphic here, 50% of all of that energy that is being used is to cool these systems down. So this brings the question of how are we managing the thermal management, the cooling of these data centers, of these AI chip stacks, to mitigate some of these issues, right? So when we look at, thermal conductivity of these heat transfer fluids, the reason this is happening is because traditional data center cooling, which often uses like air cooling, air cooling is still, I would say, the large majority in that area, but it's hitting its physical limits. There is a fundamental switch that is going to be happening, some happening now, but especially in the coming years, in utilizing liquid cooling or immersive cooling technologies. This is where you have different devices. There's single phase, two phase, direct to chip, a variety of different scenarios that can be applied here. But the thermal conductivity and also the specific heat of that working fluid are critical in determining how efficient that heat management system will be. And whenever we talk about liquids, I always like to address convection. This is something that is another form of heat transfer. So familiar, we have, of course, conduction, convection, and radiation. But in a thermal conductivity measurement, if your measurement device is not, I would say, optimal for a low viscosity liquid, for example, What you can actually do is introduce convection into the system, and this will actually result in a bias to your thermal conductivity measurement. So we always want to avoid this. One really great method for testing heat transfer fluids, liquids in general, is the THW, Transient Hot Wire. This method has a long-standing history of being used in the automotive industry, for testing of traditional coolants. It's been adopted into the EV systems, and also something that we have had quite a few conversations with groups in recent months around immersive cooling technology characterization. So the ASTM standard, ASTM D7896, this is, again, the standard that the THW conforms to. Again, this, if you see that referenced, it's related to the hot wire method in particular. Here we're just showing some data on some of the kind of standard base materials that might be used in some of these studies. Everything from ethylene glycol to glycerin to even just distilled DI water. But just kind of highlighting the fact that regardless of whether you're testing something low or high viscosity, we can test across quite a broad temperature range here, up to 200 degrees Celsius. So again, the THW is a really great option here, but it's not the only option that you have for testing liquids. When we look at the different methods here, really there's three options that we would be able to present in terms of a solution. MTPS, TLS, and THW all have some capabilities in this space. But again, there's some differences between these methods that need to be understood. For example, if you're dealing in a very novel area of material development and you're working in the low milliliter production side, maybe lab scale, maybe you don't have 50, 60 milliliters available to test with some of these other options. Well, MTPS is a really great solution. It has the smallest volume requirements of any method that we offer for liquids. Kind of going down here, again, the testing duration. MTPS and THW both have very short test times, and that allows them to measure both low and high viscosity systems. The TLS, on the other hand, is a little bit of a longer measurement. It's one that it's known to be really not ideal for lower viscosity systems. Therefore, again, if you're dealing with something more like thick and viscous, kind of think of like honey or maple syrup level consistency, sure, that could potentially be a viable option. But if it's aqueous based, you'd probably want to look at some of the others. So again, you can kind of see some of the other considerations here, but this is just, to what Adam had mentioned at the beginning, it's best to take a toolbox approach. When you're trying to fit all your materials down into one method, and you run into maybe even just some considerations around this, just around a few properties of different liquids, you can see how much that already dictates which method may or may not be better suited in that scenario. Okay, next area is textiles. I will say by and large, textiles is a really unique area of application for us here at C-Therm. And up until now, we've talked about thermal conductivity, but I want to take a second and really frame us around the thermal effusivity of textile materials and how that really leads into quantifying the warm feel, cool touch of a material property. So for some that are new, again, maybe effusivity is an unknown term. Like, what is effusivity? So really, this is defined as a material's ability to exchange heat with another body it's in contact with. You can see the units here, but really, I always like to put this little equation down so you can see how effusivity is related to conductivity, density, and CP. So these are all related properties here, but if you're still trying to wrap your head around effusivity, if you're in your office right now, there's a little kind of experiment you can do. If you take your hand and you touch your desk, maybe it's a composite desk, maybe a wooden desk, and you feel that, and then maybe you look down on your chair and there's like a metal component and you touch that. I would expect that you would find that metal feels cooler to the touch. But when you think about it, both of those materials are sitting in the room. They're not at different temperatures. It's just you're perceiving the differences based on the materials thermophysical properties. And this is really the basis for effusivity to help quantify the warm feel, cool touch of fabrics and textiles. Specifically here, the uniqueness of this capability with C-Therm is related to the ASTM D7984 standard. So this standard is really designed around thermal effusivity of fabrics using the MTPS, Modified Transient Plane Source. So when we look at some of the requirements in this standard, if this is a method that you are looking to conform to, there is no other option out there that meets all of the requirements listed in the standard. The MTPS patented technology carries a guard ring, which is again part of the unique unidirectional measurement capability of the sensor. We have dedicated textiles calibrations. It's a direct effusivity measurement, and we have tools for compression control. I'll speak to some of the other aspects here of some other new effusivity standards, specifically the ISO 22007-7 in a minute, but just wanted to kind of center us around the core standard here for textiles characterization. This is a very generic product index. You can see warm feel, cool touch across different materials. The big takeaway at this point that I'd like to mention to folks is that warmer feeling materials will have a lower thermal effusivity, while materials that are more cool to the touch, these would be the ones you want to introduce into your sportswears or summer line clothing. Those are more higher effusivity. And the note here, this was some data presented in a webinar with the University of Alberta. This is something that is really interesting because up until this point, thermal effusivity testing of these textiles are really quantified in the dry state. But what happens when we look at saturated materials? There's no standard currently that addresses this. And this was some really insightful work that the university did in conjunction with us here at C-Therm to develop some of this initial wetting data. And there's actually going to be some updates coming out around this. So if you are in the space of textiles and you are looking to really understand your materials under some representative conditions, again, saturation being one that is quite unique or I'd say quite relevant, this is something that I'd say, keep an eye out on. There'll be some updates coming over the next few months. So I mentioned the ISO standard, the -7 here, and I wanted to make a note of this. This single-sided TPS standard is simply a modification of basic TPS sensors to accommodate a single-sided or an asymmetric configuration. It's a really excellent option in many scenarios. I will say, if you're testing a higher conductivity material, something that may be, let's say, only available to produce with one piece, so you can't do the double-sided setup and you're looking to conform to the ISO types configurations, really a great option. But it's really, this is written in the standard. It talks about not functioning very well on materials below 1 watt per meter Kelvin. I would not recommend using this for more insulative materials. It is something that also has poor accuracy than the standard double-sided configuration. You see plus minus 10% here. And again, this is all directly from the standard itself. And, the single-sided setup shall not be used whenever a double-sided can be prepared. It is a good option there, but if you have the ability to do double-sided, I would go with that. And again, when we're talking about specifically textiles, most of these materials are much lower thermal conductivity compared to, again, traditional bulk, let's say polymers, ceramics, or metals. So again, just kind of understanding that what you might be calling a modified TPS is really just a single-sided TPS. Really good at what it does, but it's important not to conflate the two different methods. Okay, geothermal. This was another one where, we've done quite a bit of work with like geological applications, geothermal over the years. But in recent months, again, this is something that is coming up more and more. Testing both rocks, soils, but also some of the thermally conductive media that are being introduced in some of these systems, like thermal grouts. So when we look at thermal conductivity of these geothermal systems, the rocks and soil conductivity. This is really what drives some of the, overall borehole design, being able to test at the different level of strata, some of these cores that are coming out, testing them under different representative conditions, really give a lot of insight into the, let's say, the feasibility of using that specific area for a geothermal application. But again, even some of these, things that we are needing to introduce into these systems, like the grouts, high thermal conductivity grouts, again, comes back to these, let's say, materials that have high amounts of conductive additives in them, are something that can, if accounted for properly, can act as a bottleneck in some of these geothermal loops. So understanding these capabilities and how do we quantify them can be quite crucial. So here, just we had a quick data set. So this was some core samples that we received actually in a fully saturated state and tested them both, again, in that 100% saturated state, and then took the samples, dried them out fully, and tested them post-drying, what we call, fully dried, 100%, 0% saturation. So interestingly, you can see that depending on the type of core, the difference between saturated and unsaturated can be quite different. So again, it comes down to the assumptions that you'd be making if you're taking these core samples from a specific location. And again, testing under dry or ambient room temperature conditions only, and you want to apply that logic for every possibility of the material performance, you might be missing out on some things. And again, really understanding the real world test conditions is of great importance. So that was with the TPS. One method that is commonly referenced in geothermal is actually the transient line source for the ASTM D5334 standard. This is one that we've seen used for like aggregates. The example we're showing here, like soil testing, understanding like those loosely uncompacted materials. Technically, we're showing some data here. You can see that, the loose versus packed versus actually a little bit of saturation. And again, kind of demonstrating that change in thermal performance under those different conditions. But you can imagine like this sample type here, this soil loose material, you can very easily insert the TLS probe down into it. But if you're dealing with something like a core, something more solid, there are ways of measuring those with the TLS. It requires drilling a bore or a guide hole, I should say. But there are often more easier approaches to addressing that. Also, when we're looking at the geothermal grouts, those conductive paste type samples, TLS is one that is being used quite extensively in this space as well. All right, and then on the way to wrapping things up with the final application here, which is hydrogen storage, specifically some of these metal hydrides. So in hydrogen studies, these metal hydrides are of really the centerpiece of what a lot of folks are looking at. But again, just like many of the samples we've talked about, the conditions that you test them in can be very important in understanding their true performance. Hydrogen atmospheres, high pressures, high temperatures, these are all, let's say, environmental variables that are being investigated on these materials. And we've developed two really strong solutions for testing metal hydrides. Comes down to the different formats that the materials are in. Is it a powdered or is it a pelletized sample? Depending on which one you're dealing with, this will infer which method to use. The TLS for the powders and the TPS for the pellets. So I just want to share some of this data. This was some work that was done in conjunction with UQTR, University here in Canada, but really nice example of demonstrating that these samples under different environmental conditions, so these were done in a specialized high pressure cell, going from vacuum to ambient to vacuum to then subjecting it to a certain pressure of hydrogen, how drastically that changes the effective thermal conductivity. Again, by adjusting those conditions, you can kind of see that how it cycles and is very repeatable. It goes back to that initial base point in a vacuum and then again right back up under those hydrogen conditions. So this was some of the early work. Again, there's a lot of folks that are really pushing some of the envelope in how this work is being, or what work is being done in this space. But testing of pellets, For hydrogen storage media, metal hydrides, the TPS is a very great option there. But also, again, for the powders, again, the different formats here, again, you can see a different scale in the overall thermal conductivity, but the idea still holds that the different conditions significantly are impacting that effective output. So all that is to say is when you're looking at metal hydrides, being really able to test under that hydrogen environment becomes critical to truly understanding how that material will behave. So just to kind of wrap things up here, going into a little bit of an outro, the Trident provides really, again, a multi-method approach that provides rapid, versatile testing across a variety of materials to quantify their thermal performance. As we've demonstrated here, this was kind of like, I would say, a little bit of a rapid firing of some of the more popular use cases and kind of the innovations that we're seeing. But, the different conditions, whether it's temperature, pressure, saturation, being able to test under those representative environments is really important. And in some case, it can be, I would say, almost, it'd be without that, the results aren't going to be effectively even usable. The other thing, and you could kind of take that with the same idea, is mimicking aging or limit testing. So when you're subjecting these materials to these different conditions, being able to cycle them repeatedly or understand how that is going to affect that, let's say that long-term performance is also something that can be looked at, and would recommend doing so. But that being said, that kind of brings us to the end of the formal content here from the application side. I'd like to thank the folks for joining here today. Also, Dale from SciMed for being here. I will just kind of wrap things up with a few final announcements here as we conclude today's session. If this type of content was interesting to you, we do have a variety of additional resources available on our website. Past webinars, tech libraries, definitely feel free to check that out. Adam had mentioned some of the upcoming webinars as well. So we do have another guest webinar happening March 16th, where we'll be looking at thermal properties with high frequency, frequency time domain thermal reflectance techniques. Start of April, my colleague Genesis, who is the lab manager at Thermal Analysis Labs, will actually be doing an educational series on DSC, methods and applications. And then April 23rd, Alex, who also works in our Thermal Analysis Lab group, will be doing a TMA 101 session as well. So as was mentioned, and if you saw the intro video there, C-Therm here, we have, of course, focused on thermal conductivity. In North America, we also support Rigaku and Metrovib for their unique line of products, and Thermal Analysis Labs is our contract testing division. So if there was any need, depending on where you're at in the world, for any additional material characterizations or testing services, these are things we are certainly happy to provide. If you'd like to learn more, again, we offer free technical consultations, gives you a really nice opportunity to meet with us and discuss your applications and testing needs, give you some live demonstrations of the instruments even. These are all things we're happy to set up, so please feel free to reach out if that would be of interest at all. And also, of course, if you like what you've seen today, and you're just looking maybe for some budgetary information, if you'd like a quote, again, these are all things we can send along. Just drop us a message there or reach out to us via email or on our website. We can get back to you with that content. Last note here. So if you're coming from the academic industry, I will just always flag that we do offer academic support programs. Definitely feel free to reference the fact that you're coming from an academic institution. You can kind of see some of those benefits that we offer there. More than just a kind of an academic discount, there are some nice additional features that we present within these options. And if you're not already doing so, give us a follow on LinkedIn, and also more recently our YouTube channel. Subscribe. We're posting a lot more application featured content. Some of the kind of the snippets of some of these larger format pieces. Just a great way to kind of keep up to date on upcoming webinars, videos, and blogs. This is where it's all going to go first, so check that out and give us a follow if you're not already doing so. But that being said, that brings us to the end of the formal session here today. For those that are sticking around for the Q&A, please feel free to do so. If you have to jump off at this point, again, from my side and speaking for Adam, thank you for joining today's session. Thank you, Dave, once again for joining us here. And hopefully we'll see you guys at the next one.